So derivatives will stay just as important as they are now. All right, so what we're talking about today, increasing, decreasing, and concavity. And we will be using the first and second derivative to actually describe our original function. So this is an algebraic definition here, and I have just a quick sketch of a graph that I'll show you. But here it says, let f be defined on a given interval, and x sub 1 and x sub 2 will denote points on this interval. So basically, when you look at a graph, you're reading the graph from left to right. So these are your x values as you are moving from left to right. Okay, so we are going to describe the graph in 3 different ways. The first is that our function f is increasing on a given interval if f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2. Okay, that seriously makes 0 sense to me. So what this is saying here is if this is your first x value, which is lower because you are reading from left to right, then your second x value, when you plug those x values into the function, they're saying that the y value for the first one is smaller than the y value for the second. So basically what's happening is your y's are increasing, meaning your y values are going up. So let me show you this quick schematic. So here, if you have your first x value and your second x value, you plug those x values into the function and you would plot these points. They're saying that your first y sub value that corresponds to this x is lower in value than this y sub value. So then if I were to sketch this graph, this function would be increasing. Agree? Going from smaller to bigger? Yes? Okay. So that's all that's saying in mathematical terminology. All right? So then they're saying in the second portion of this definition that f is decreasing on this given interval if your y value for your first x coordinate is greater than the y value for your second x value. So what this is saying here is that the y's are decreasing. Okay? And then the last one here is that f is considered constant if your two y values are equal to each other for these given x points. Okay, so this is what we're talking about graphically, and I'll just start from the bottom, so we're going to go from right to left, which typically you don't. F is constant, so this would be your constant graph if your y values are equal to each other. Okay, so that's what this is saying right here. Here, we said that our first y value is greater than our second y value. Okay, so your function is decreasing here. So this is what it would look like graphically. And then in our last one, which was really our first, you're saying that your first y value is smaller than your second y value, therefore your function would be considered increasing over that interval. Okay, so these are definitely important. Now, you will sometimes be given some information about a function, but you will not be given the function. So it's important that you understand the vocabulary and what they're talking about. So in this first theorem, you're given some vocabulary that you need to make sure you're aware of. And here it says that we're going to let f be a function that is continuous on a given interval and differentiable on that given interval. Okay, so the first piece here is that our function is continuous, meaning you have no gaps, no vertical asymptotes, no holes. In plain English, which you cannot use as a justification, you're basically going to sketch this function on that closed interval from A to B without lifting your pencil. You cannot use that as a justification. Okay, some of you have, but you can't. Okay, because it's not math. That's drawing. Okay? Then it says that the function is differentiable. What that means is that you can take the derivative. It doesn't mean that they gave you the derivative. So you might be given some information about a function that would say f is continuous on the closed interval from 1 to 7 and twice differentiable. What that means is you can take at least the second derivative. Okay? So this information is important because in order for us to speculate about f, using the derivative, we have to be able to take the derivative. If your function is, let's say, the absolute value of x, which we know is our v-shaped graph, okay, where is that function not differentiable? At 0. So what if 0 was part of my interval? Wouldn't that function not be differentiable over that interval then? Okay, so do you see why it's important to kind of know the information even if you don't know what the function is? Okay, so that's what they're giving us, that information. So, in this theorem, if our function that we are given is differentiable and continuous, then f prime of x, if we find f prime of x, and f prime of x is greater than 0 for every value on that interval, meaning our derivative is positive, okay, then f, meaning the original function itself on the closed interval, is considered to be increasing. If our derivative is less than 0, f prime of x is less than 0, meaning the derivative is negative on every value or for every value in that interval, then our function is considered to be decreasing on that interval. Decreasing. And then the last one is if our derivative is equal to 0 for any or all values on that interval, then our function is considered to be constant on that closed interval. Okay, meaning it's just going straight across. Okay, so these here are really important that you know, and we're actually going to apply them. So here you're given a function, and what we want to do is identify where this function is increasing or decreasing. And you are going to be identifying where this is in interval notation. And we're also going to practice writing the justification, and then I'm going to give you 4 specific terms that you need to avoid when you're justifying or giving any explanation about f of x. Okay, so make sure you leave a little bit of room somewhere. So when you are going to identify any intervals or you're going to talk about increasing or decreasing for a function, the first thing we want to do is find the critical numbers. And I'm going to use CN as my abbreviation. So if you go back to pre-calc and you think about when you guys had the rational function inequalities, you actually had to identify, let's say specifically where your quotient was greater than 0. You were looking to see where that quotient was always going to be positive. So you had to identify critical numbers. And we talked about this at the beginning of the year just a very little bit. But critical numbers basically take your number line and break it up into intervals. So first of all, is this function continuous? Yes. You have a cubic function which technically would go, I think, like this if you're looking at me, right? Okay, and it goes from negative infinity to positive infinity. That's the domain. Okay, so what we want to know is, over that domain, even though we could kind of picture what's happening, where is this function increasing, where is it decreasing, and what's kind of happening so we can get a mental picture because we're not using a calculator. Okay, so this is what we're going to do. To find the critical numbers, we're going to set f prime of x equal to 0. Okay, so that's our first step. We need to find f prime of x. So f prime of x is equal to 3x squared minus 6x. Everybody good? First derivative. Okay, then we want to factor and set this equal to 0. So how would I factor that? Just take out an x? Yeah, take out a greatest common factor. Take out the biggest thing. In this case, we've got a 3x times, what is this, x minus 2, and we're going to set that equal to 0. This is our derivative. Okay. So we're going to find our critical numbers, which in this case are what? Just 2? 0. So x is equal to 0 and 2, and these are the critical numbers. Okay, whenever you identify critical numbers, they are x values. You would state x equals. Don't just give me 0, 2, 5, 7. Well, I mean, what is that? Okay, you got to tell me what it is. So what this is going to do for us is actually split up our number line from negative infinity to positive infinity, and we're going to put 0 and 2 on here. So first or second unit, I can't remember which one, we talked about multiplicity. And we use this to speed up our process in identifying the intervals over which our function was positive or negative. So I'm going to show you how that works, and I'm also going to give you more detail when your multiplicity is even. So remember what multiplicity is. Multiplicity is the number of times a 0 occurs on a graph. So in this case, this quantity x minus 2 is to the first power. So you would describe multiplicity as either even or odd. So 1, is it even or odd? Odd. 3x to the first power, even or odd? Odd. When your multiplicity is odd, your signs will alternate from positive to negative starting on the right-hand side. Okay? So these are both odd, so that means this is going to start positive, This would be negative. This would be positive. Now I'm going to prove it to you. Watch. You pick any value in this interval. Pick an easy number, guys. Don't pick like 100. Okay? So I'm going to pick 3. So when I pick 3, you want to plug that value in to the factored form. Why? Because it's easier to do the math. We do not care about the value. We care about the sign, S-I-G-N. So when I plug in 3, 3 times 3 is positive. 3 minus 2 is positive. A positive times a positive is positive. Plug in 1. 3 times 1, positive. 1 minus 2, negative. Positive times a negative is negative. Does everybody see how that works? I will show you when we have even multiplicity what happens. Okay? But this makes it a lot faster. The explanation obviously is longer, but you could do this a lot quicker. So this actually will help us when we're talking about increasing and decreasing. So here, when our when f prime is positive, this is where f prime is greater than 0, f prime is greater than 0. That means f of x graphically will be increasing on these intervals. Where f prime is negative, f prime is less than 0. This is where f is decreasing. This right here is your justification for this. This is your justification for this. Okay, so now we're going to describe. So remember, you need to leave a little bit of room for the terms that I am telling you not to use. Okay, but we're going to go up here. So this is going to be our answer. This is the work. This is your answer, and you would answer in sentence form. F of x is increasing, and we're going to give the intervals where our derivative was positive. So in this case, we're going to go from negative infinity to 0 using parentheses. You can use a union or not. It's up to you. And then from 2 to infinity. And your justification is because f prime is greater than 0. Okay, so when we're talking about increasing, we are looking for where the first derivative is positive. Then you would say f of x is decreasing from 0 to 2 because f prime is less than 0. Okay, questions before I go on to what you need to avoid using? How we got anything here? Why we wrote something? Now, you won't always have to justify your answer, but sometimes it will say, justify your answer. Less is more. Do you see I didn't write this crazy long sentence? I didn't talk about critical numbers. Okay, this right here is just a testing number line. You cannot use this. Don't say see the number line. That's not a justification. This is not universal. This is just a test. This is what's universal right here. Okay? All right, so ambiguous words to avoid in your justification. What's the first one that you can think of that I always talk about?
It.
Ah, yes. It. Bless you. Not specific. It means nothing. What is it? It could be anything. Okay? Second, derivative. Don't just say the derivative is positive. First derivative, second derivative, third derivative, eighth derivative. What are you talking about? F prime, F double prime. Okay? Use the notation. It's less to write. You're saving ink or pencil, whatever you're using. Okay? Third, slope. Slope of what? Slope of F, slope of F prime, slope of F double prime. Okay? You can have the slope of the slope of the slope of the slope. Oh wait, of the slope. Okay, you just keep taking the derivative. It's the slope of the previous slope. So you have to be specific. And then the last one is graph. Okay, first of all, what graph? I don't see a graph. The graph of what? Use the notation. F of x, F prime, F double prime. Okay, before we go to the next page, does anyone have any questions about this first page? Are you sure?